Choosing U, substitution method. In general, for the types of problems we're concerned with, there are 4 cases. We choose U to be one of the following. Number 1, the quantity under a root or raised to a power. Number 2, the quantity in the denominator. Number 3, the exponent on e or other base. And number 4, multiple trig functions. Remember that some integrands may need to be rearranged or rewritten to fit one of these cases. And we'll see one in the next example. Can we use substitution? Well, let's see. If we let U, we don't have much there, so if U is cosine x, so then we'd have U cubed, then the derivative of U with respect to x would be du dx. Derivative of cosine x is negative sine x. But we don't have any sine x. Oh no, what to do? Well, let's see. Cosine cubed x is the same as cosine x times cosine squared x. And I remember some formula that went sine squared x plus cosine squared x equals 1. I think they call that Pythagorean theorem. Well, we could isolate cosine squared x by subtracting sine squared x from both sides. And now we have a way to replace. Right? So now we have cosine x times, we're going to replace the cosine squared x. So we rewrote cosine cubed x to cosine x and 1 minus sine squared x dx. Right, so we have that. We could distribute the cosine x, so that would give us cosine x minus cosine x sine squared x, and this is all dx. Now, there's no problem with the cosine x. That's easy integrating. So let's split this up and have cosine x dx minus the integral of cosine x sine squared x dx. And now we can do substitution because u would be sine x and the derivative of sine x is cosine x. And let's take a look at that at the next page. I actually have it all done for us. All right, so we have cosine dx minus cosine x sine squared dx. Now we can do a u substitution for the second piece. No problem integrating the cosine x, that's just sine x. And then we now have u is sine x, du is cosine dx. We'll replace the sine squared x of this part here. This part here, just the sine x is replaced with the u. The cosine dx is replaced with du, and we just raise u to the second power. So now we can undo the power rule. So we increase the exponent by 1, divide by the same thing, and don't forget plus c, because when we take the derivative, the constant gets lost. So now f of x is sine x minus, once we substitute back, sine x cubed divided by 3 plus c. So the moral here is break up the sine squared x, cosine squared x, sine cubed x, etc. using Pythagorean theorem, and make sure you choose u to not include the exponent. Right? So that's my little moral in this one. On these ones, we could take the derivative and put it all back, but because we did all the checks on the last couple videos, on this one, I'm just going to do straight integrating. All right, so now this one. All right, so if you're like me, you only bothered to learn one Pythagorean of the Pythagorean theorems, right? Sine squared x plus cosine squared x equals 1. Because I can get all the rest of them just by dividing. Well, tangent x is sine divided by cosine. So I'm going to divide everything by cosine squared x. So now sine squared x divided by cosine squared x is tangent squared x. Cosine squared x divided by cosine squared x is 1. And that's just the reciprocal function for cosine, which would be secant. And there we go. All right, so now we have a way to rewrite this, because if we made u tangent x, what are we going to do? Right? We don't have the derivative. We don't have the du for tangent x, right? Because the derivative of tangent x is a secant squared x, and there was no secant squared x. All right, so now we're going to rewrite the tangent squared x as secant squared x minus 1. All right, so now let's take that derivative instead. So now we have let's take that derivative instead. We have not derivative, integral. That integral instead. So secant squared x minus 1 dx. This one is no longer a substitution because we can, I'm going to split this, but we can integrate both of these. So we have secant squared x dx minus dx. Whose derivative is secant squared x? Why, that is tangent x. And then whose derivative is dx? That would be x plus c. And there we go. So f of x equals tangent x minus x plus c, with the help of Pythagorean theorem. Right. Find f of x so that the derivative is negative 4 e to the x minus 6 sine x. So we're given that, so that's the derivative. We want to find who has that function as its derivative, which means we want to integrate. So we're going to integrate the negative 4 e to the x minus 6 sine x dx. We actually don't need any substitution on this one, but I threw it in here. Negative 4e to the x dx. I like to split these integrals up. Minus 6 sine x dx. You could also factor out, and we can put f of x equals. I don't like to put that if I'm going to switch to u's, right? Because then I got x's and u's together, and that's not right. But when we integrate, we get the function whose derivative we were given. And you can factor out coefficients, that's no problem. All right, so we want to integrate e to the x. Why, that's pretty easy. So we have negative 4e to the x. It's nice being your own derivative. And then we want to integrate the sine x dx. So whose derivative is sine? That would be cosine, but negative cosine, right? Because it should be negative sine. Right, so the derivative of cosine x is negative sine x. Well, now we've got two negatives, so our equation now is going to be negative 4e to the x plus 6 cosine x. Oops, why is there a dx? No dx. Plus, so f of x is equal to negative 4e to the x plus 6 cosine x. And there we go. And if we were to integrate, right, or excuse me, if we were to differentiate, the derivative of negative 4e to the x is negative 4e to the x. The derivative of 6 cosine x is negative 6 sine x, which is just what we had before. All right, so now let's find this one. And we should distribute the secant x. So we have secant x tangent x. And actually, let's not only distribute, let's split this up. So secant x tangent x dx plus the integral of secant x times secant x is secant squared x dx. Now this one also does not need substitution. I've now given you like 3 where we didn't need substitution on a substitution lesson. But sometimes it's a good idea to throw in some other ones so that you don't think every single time you see multiple trig functions, what you should do is substitution. Right? Because if you make the u tangent x plus secant x, well, you don't have the du. But when we distribute, we see, we know whose derivative is secant x tangent x. Right? That's secant. So f of x equals secant x plus whose derivative is secant squared x? That's tangent x. And we're done. And then plus c. Don't forget the plus c. Did I remember the plus c in the last one? No, and nobody said anything. Plus c, because when we take the derivative, we lose the constant. So when we integrate, we got to put it back. Right? We have some constant that was lost. I think that was the only one I forgot to see on. Let's try the next one. All right, so we have 1 plus sine squared x times cosecant x. All right. Why don't we rewrite this one first? Right? So don't always, if you go to right away to substitution, see if you can rewrite things and make it better. All right. So we could rewrite that cosecant. Right. So we have here the integral of, and it's 1 plus, and so it's 2 terms. So we have 1, and I'm going to split this up, 1 d theta plus, then we're going to integrate the sine squared theta times cosecant theta is the same as 1 over sine theta d theta. Well, now that's pretty easy, right? Because now we have the integral of, I could just write d theta, plus the sine, one of the sine thetas are going to cancel, right? So I'm just going to have the integral of d theta plus sine d theta, sine theta d theta, right? Well, the integral of d theta is just theta. So f of theta equals theta, and whose derivative is sine theta, that would be negative cosine theta plus c. Right? And if you took the derivative of theta, you'd get d theta. If you took the derivative of negative cosine theta, you'd get sine theta. And they made it tricky for us by adding a cosecant theta in there. But we were able to figure that out. Right? So you are allowed to simplify. All right, this one's just a straight substitution. Right? So the u is the thing in the radical. Right? So x squared plus 1. The derivative, so du dx equals 2x. Don't see a 2, right? So we've got to multiply, first of all, multiply both sides by dx. So we have du equals 2x dx, and we'll divide both sides by 2. So 1/2 du equals x dx. All right, so this part here is u, and the x and the dx become 1/2 du. All right, let's integrate. Let's rewrite it, and then we'll integrate it. All right, so we have 1/2, which we could factor out, times u. We need to rewrite that as an exponent to the 5/6 power du. All right, and now just integrate it. So that would be 1/2 times u, add 1, so that would be 5/6 plus 6/6, that's 11/6. And you're going to divide 11/6, not 11/16. And you're going to divide by the same thing, plus c. Dividing by 11/6 is the same as multiplying by 6/11. And that will cancel. Right, so f of x equals, right, so we're going to have, actually let me write it one more time over here, the nice cleaned up, and then we'll substitute. That would be 3/11 u to the 11 6 plus c. Right, so now we'll substitute back. So that would be 3. I'm going to leave it as an exponent rather than rewrite it as a radical. So 3 times x squared plus 1 to the 11 6 power, all divided by 11, plus c. There we go. And we're done. So once you get the hang of these, they're not too bad. You just have to remember when you use substitution and when you can just rewrite it, and when you need to rewrite it before you use substitution. All right, so denominator, right, is going to be your u, not the numerator, because otherwise you'll never be able to get anything into the denominator. So the u is going to be 3p minus 1. Okay, won't include the exponent. The exponent's not the issue. It's the 3p, it's the fact that something's in the denominator. So, and it's a function, not just a single variable. So u is 3p plus minus 1. Du dx, or excuse me, du dp is equal to just 3, right? Let's multiply both sides by dp. So we have du equals 3 dp. We have a 9 dp. No problem, right? So you can be off by a constant multiple. That means 3 du equals 9 dp. Oops, not pd. All right, so the 3p minus 1 is going to get replaced with a u. We're going to change that to a negative exponent. And the 9 dp will be a 3 du. And now we're good. So we have the integral of 3 times 3, u. You did not look at the problem. Look at my u's. So 3 u, come on you. Come on you, there we go, to the negative 3 power du. All right, so now we can factor out the 3 if we like, or just do it as we take the integral. Let's just do it as we take the integral, since we didn't write the 3 on the outside. All right, so this would be 3u, increase the exponent by 1, so that would be negative 2, divide by the same thing, and don't forget the plus c. And now we'll substitute back, and now we'll write it in terms of p. So f of p equals, let's write that as negative 3/2. And u is 3p minus 1 to the negative 2 power plus c. Let's clean up that negative exponent. F of p equals negative 3 divided by 2 times 3p minus 1 squared plus c. And there we go. We're done. All right, all done with this one. Let's do another one. All right, so we've got a something raised to the power. The stuff on the inside will be the u. X squared plus 2x plus 1. Du dx is 2x plus 2, right? The derivative of x squared plus 2x is 2x plus 2. All right, we've got everything we need. Let's just move the dx over. So du is 2x plus 2 dx. So this is replaced with the u. This is replaced with the du, and then we just integrate. So this is a nice, easy one there for you. So this is u cubed du. So this is in terms of x. So f of x equal, actually, excuse me, let's do the integrating. Then we got to do the substituting. Don't write f of x yet. U to the 4th increased by 1, divide by the same thing, plus c. Now let's write in f of x. F of x equals, because we're going to do the substitution, and we've got x squared plus 2x plus 1 to the 4th power divided by 4 plus c. And we're done with this one. Another one done. All right, so again, something to the power. The inside is going to be the u. So u is x cubed plus 3. The du dx equals 3x squared. Okay, we can move the dx over. So we have du equals 3x squared dx, but we don't have a 3. We have a 2. So how do you make a 3 become a 2? You're going to multiply by 2/3. So 2/3 du equals 2/3 times 3x squared dx. So 2/3 du equals 2x squared dx, and now we match just fine. So you can be off by a constant multiple, right? Because constant multiples sometimes get canceled when we're taking derivatives. Right? So we're going to replace this part with a u and this part with a 2/3 du. So long as everyone's represented in that equation, we're good, and the exponent stays. So we have the integral of, I'll put the 2/3 in front this time, so 2/3 times the integral of u to the 3/2 power plus, times du is what I meant, right? So you see the u to u substitution, it makes the equation so much easier. So all you're doing is a little power rule. So this would be 2/3, and then we increase the exponent by 1. Right? So that would be 5/2. 3/2 plus 2/2 is 5/2. And then divide by the same thing. Right? And then plus c. So dividing by 5/2 is the same as multiplying by 2/5. So that means we've got 4/15 u to the 5/2 plus c. And now all we got to do is substitute the u back. Substitute the x cubed plus 3 for the u. So f of x equals 4 times x cubed plus 3 to the 5/2 power, all divided by 15, and don't forget the c. And we're done with this one. Another one done. All right, so here cosine's not raised to a power. What's raised to a power? It's x. All right, and so our u should be what's raised to a power. All right, so u is going to be, I'm going to write that as x to the 1/2. Right, so du dx equals 1/2 x to the negative 1/2. Right, because this would be a chain rule. Somewhere there should be the derivative of the inside part. So, and if there is, then we can integrate by undoing the chain rule. So du equals 1 divided by 2 square roots of x, or you can write it as dx, or you can write it as du equals 1 over 2 times x to the 1/2. Either way, dx. But we can see that we're missing a 2, right? We're missing a 1/2. So now let's multiply both sides. Actually, I like the one up here. It's not like I'm substituting the square root of x back for anything. So we're going to multiply both sides by 2. That means 2 du equals 2 times a half will cancel 1 over the square root of x dx. So we're going to keep the cosine. We're going to replace that square root of x with a u. We're going to replace the square root of x and the dx with a 2 du, because there must have been a 2 to cancel out the 1/2. Right? And the 2 can go in front. Right? So now we have cosine, so 2 times the integral of cosine u du. Right? And whose derivative is cosine? Why, it's sine. Right? So 2 sine u plus c, and we'll replace the u. So f of x equals 2 sine square root of x plus c, right? And then if we take the derivative, right, the sine becomes a cosine, and then we would have to take the derivative, it's a chain rule, of the square root of x, which would give us the x to the negative 1/2 when we multiplied it by the 2 there. All right, let's do another one. All right, so, and actually I'm going to do this one on the next video. So we've got some unique problems here. This one, what happens when we have 2 terms in the denominator? All right, because we can't just divide. All right, so I'll see you in the next video. Bye for now.